So with that, let me start today's session. So good afternoon and sorry for the delay. So today I will be talking about week 5 assignments. So what we have done last year. So what the questions were given last year. So we'll be discussing that here. Few of the questions from the last year. So we'll be discussing from some 8 to 9 questions, and then you can use these concepts to solve the questions which are given in the this year's assignment. So with that, let us start today's session. So the first question which is given in that last year question assignment is that in serial manipulator, the velocity vectors of the individual joints can be obtained by backward propagation. So let us first understand what is backward propagation. So if you see uh, so if you talk about a serial manipulator, so suppose these are the one of the example of a serial manipulator, and this is just fixed. So what we are talking about, we are talking here about that if we are given this x position of this end effector or x dot, rather we can this velocity vectors, that is x dots of the individual joints, can be obtained. So the initial joints, the velocity of the each of the joints can be obtained from even if this is given. So now what we know that x dot is whatever you study, that x dot is nothing but j of q, that is Jacobian, and q dot, right? So this is how. So to this is the way which we find. So given the joint parameters, we try to find out the uh, velocity in the actual workspace, that is x dot. Now the question here is that can we do the reverse? So that is using backward propagation. So for that, what we have to find out, we have to find out j inverse q, and we know that most of the times j of q is what, a rectangular matrix, rectangular matrix, and and in that case there won't be any inverse which will be existing, right? And also in that case we can use pseudo inverse, but that is not the case always where we can find pseudo inverse of a matrix. So that way we cannot basically invert this. So we cannot uh, write j inverse q x dot always, right? Always no. So this is what. So the statement says that we can do we can, where is that? So we can obtain with backward propagation individual joints velocity factors of the individual joints can be obtained by backward propagation. So that is not true always. So the correct option will be false for this question. So this is how we deal with this question. So let us move to the next question. So next we have MQ. So it's given that MQ is the inertia matrix. So and JQ is the Jacobian matrix. What will be the inertia matrix in task space? Now, so let us first derive this and then we'll try to find what is M mu. Okay, so you know that uh, mu dot equals to nothing but J of Q dot, right? And T is equals to J of Q, this transpose, and F, right? Now, if we take the double derivative, what we'll get? We'll first differentiate J, keep this as constant, and then what will happen? We'll then have J of Q and Q double dot, right? So what will happen if you try to write this? So further, if you write, you will get Q double dot equals to, so this will go this side. So you can write mu double dot minus J dot Q dot. Okay. And if you take this bracket, then you have to write here J inverse of Q, right? So from this we'll get this, right? So Q double dot. Now we know that this general equation for the motion is m of Q double dot plus n Q dot equals to Jt of q f, right? Now, if we substitute this q double dot here, what we'll get? We'll get m of q, and you just substitute the whole thing here, this whole thing. So what we'll get? You will get, take this bracket, J inverse q mu double dot minus J dot q dot, this is closed, plus eta q dot equals to Jt q f, right? Now, suppose you have to write it in the terms of f. So what we'll take? We'll move this to this RH, LHS, and then that what we have to do? We have to take the inverse. So that will become what? J inverse J minus T, right? So this will become J minus T if it goes here. So how will you write? So J minus T of Q and this whole thing multiplied to this whole thing, right? So that will be nothing like MQ and then J inverse Q M double dot, sorry, mu double dot minus J dot Q dot plus J inverse J minus T Q eta Q dot, right? So if you further see this, what you'll get? F equals to J inverse J minus TQ MQ J inverse Q mu double dot plus and so on. So just we have expanded this, what we have written here, right? So what you can see, this is nothing but what? Some another M matrix in terms of mu, right? This is nothing but mu because this will become what? Mu double dot. So this is the inertia matrix in task space. So what is that? J inverse J minus TQ, MQ, and J inverse Q. So this is the matrix which we are looking for. So, and which is nothing but M of mu. So here M of mu is J minus T, mu MQ, and J inverse Q. So which one is that one? This one, right? So this would be correct. Right. So this is the inertia matrix in task space. So this is how we solve this question. So now moving on to the next question, we have what? We have inertia matrix. So it's basically based on the property of the inertia matrix. So the statement is is that inertia matrix is always positive and symmetric. So the first part is pretty much clear that inertia matrix is always positive, right? Because all, so we know about this inertia definition is that only the moment of inertia of any body around the axis which will be what? Positive, right? So this is always the case. Now whether it is symmetric or not, that you have to also think about. So when we talk about inertia matrix, we will have this entries like what? We have moment of inertia in x-axis compared to y or z, right? That means x-axis y-z, then we have a ixy, here ixz, then here we have yx, here we will have yz, and then here we'll have yzx, zx, zy, right? So these are the entries of inertia matrix. Now you can see that these and this. So this is basically, if you understand, these are called what? These terms are called nothing but it is called as product of inertia. Or rather, these are nothing but if you physically understand, this is just moment of inertia along xy axis and this is along y axis. That means the same. So what does that mean? That the value which will calculate will be also same. So these are always true, right? So yzx equals to ixz y. What is left now? Yz equals to zy, right? So if you take transpose, we will get the same thing, right? So that means what? I equals to it. So basically it is symmetric as well. So what? So first we see that it's positive and it's symmetric. So whatever the statement is telling here, that in SI matrix is always positive and symmetric, that means it is true. So the correct answer for this question is true, right? Now let us move to the next question. The next question is that linear acceleration model of a rotatory joint. So this can be seen from two ways. So let me explain this in one way, and the second I will give a hint how you can see that. So suppose you have a link here. This is I plus 1. So what you can be given, this A will be given here, right? So A in terms of I, then alpha will be given in I. This means alpha of I frame, ith link into the ith frame. Then A acceleration, linear acceleration will be given in the ith frame. And this will be P. Suppose it's given from I plus 1 to I. So as you have seen earlier, in the case of velocity, you can similarly transform this linear, or rather this velocity, joint velocity, to get the joint velocity at I plus 1, or rather the velocity at I plus 1. Right. So how can you do that? So here, but we are looking at for the acceleration. So similarly for acceleration also you can just transfer. So looking into here, how can you transfer that? So suppose AI is given, so that will be added. So AII plus what will have been given. So now this alpha into P, alpha cross P element will be added. So right. So then you can see that alpha, or rather this component is known as what? This is nothing but tangential. So this is, so if you have a link, so there will be one tangential. So this one is tangential and one is along the line. So this is nothing but the tangential, and then the next is the along the line component. So that can be given by nothing but the Coriolis part. So that is I omega I cross I omega I cross I plus 1 and P. So this is that part, and this is this thing, this is tangential, and this will be translated. So from I to uh, I plus 1 link. Now, so these all are in what? So this is all are in I frame. So you have to get it into I plus 1 frame. So you must multiply everything with this I plus 1 or rotation matrix. So in that way, how will you get? So these all I. So everything is in the terms of I, and then we are converting that I into in terms of I plus 1. So now we'll get acceleration from I plus 1 to I plus 1. So this is the way in which you can say that how this linear acceleration model will look like for a rotatory joint. So which of these is correct here? So you can see here I plus 1 R and A, and this is that part, the tangential, and this is the another thing, another part. So this is the correct answer. Now the another way in which you can solve this. So let me this another way in which you can solve this. So earlier during the velocity propagation, so we have also seen this V I plus Y I plus 1, right? So that is nothing but similar to this, right? I plus 1 to I V I. That means whatever V is available here plus the effect of this link length. So and omega. So I omega cross I P I plus 1. Right. So this was how we can write V I plus 1 to I plus 1. So now A is nothing but v dot, right? So you can differentiate this, right? So if you take v dot I plus 1 to I plus 1, so this will not change. And you can take the differentiation of this part. So you can use chain rule, and then if you do the differentiation, you will get the same thing as we have discussed here. So this you can try to do by yourself and see whether you will get the same result or not. That is nothing but this one. So the linearization model of a rotatory joint is given by 2, that is I plus 1 to I plus 1a, nothing but this a translated with this tangential term and then normal term. So this is how you get this question. So now let us move to the next question, which is nothing but in a single rotatory planar link manipulator, the motor connected with a rotatory joint is rotating at a uniform speed. So first, let us draw what it is given in the statement. So it's saying a single rotatory. So if there is a rotatory, something must be, there is an axis about which it will rotate, right? And it's a single planar. So this is the case. So this is must be the base, and here will be some end effector. Now this is rotating, right? Okay, with what? Omega, and that is nothing but 2 radian per second. So till here it is clear. Now, and the distance between the base frame and the end effector means this distance is given as 0.5. Okay, so 0.5 is the distance between end effector and the base. And it's asking about the centripetal acceleration. So you know that centripetal acceleration will act what? Inwards, right? Now here, now if you write centripetal acceleration formula, what will be the formula? M centrifugal force is mv square by r. Now we don't have v, but we know that v is nothing but r into omega. So we know r. So r is 0.5, omega is 2, right? So further, so this is what centripetal force. So you can write Fc equals to mass r omega square by r. Now we are only interested in acceleration, so no need to look into the mass. So you can just write r omega square by r, right? So that is nothing but r square omega square by r, that is r omega square by r omega square. So that will be equal to what? So we have 0.5 as r, and omega is nothing but 2 square. So that is 2. Now this force is directed outward. So, but the centripetal force is defined in inward. So, the correct direction of this acceleration will be, we have to make minus. So this will be become minus 2 meter per second square, right? So the correct answer for this is minus 2 meter per second square. So this is how you get the acceleration, that is rather than the centripetal acceleration or the radial acceleration component of the end effector, right? Now moving to the next question. Now we have the specification of a robot as a function of time is called as a trajectory. So this is the statement which is given. So it is saying that a robot position, or rather x, is a function of time, right? And this is known as trajectory. In fact, this is correct because the trajectory means that if you are moving from one place to position, how you are moving. So that means at each time you have this x function of x with respect to time. So you can say that if we follow some trajectory, or rather this trajectory gives that what is the states, or if x represents the states, or in what position it is based on the time or where it's have started. So this is the correct definition of trajectory. So it is true. Rather, if this is not in terms of time, if it is not in terms of time, then it is uh, and further, if it is in the form of some parameters. So suppose if you have 0 to t, if you're looking, if we convert that to 0 to 1 or 0 to as some parameter, 0 to 1, and in some s domain, so in that case it is called as path, which you might have studied. this year, this fifth week lecture. So, but here, here it is telling time, and so it is trajectory. So that is the difference between trajectory and path. So if it is with respect to time, if you have x, then it's trajectory, and if it respect to some s different from time, which you have got in another domain, then it's called as path. So here it is true, as we have x in terms of time. So correct answer is true for this question. Now, moving on, we have question number 7. So here we have for a given manipulator, we have ith joint. So angular velocity. So angular velocity is omega, and this saying ith means what? This one is given I omega omega, right? So omega in terms of I is given, that is nothing but 0, 1, 2, right? And acceleration vector is given, that is alpha is given. And what is that? So alpha I is given, that is 0, 2, and 1. And what else is given? P is given. P is given is I plus 1 to I, that is 2, 0, 1. Now it's asking for tangential acceleration. So what is tangential acceleration? So earlier in this question, we have got an equation for linear acceleration, and this is tangential, and this is nothing but radial. So they are asking for tangential. So let me again write that equation, and then we can solve it. So I plus 1 to I plus 1 A is nothing but uh, I plus 1 R to I plus I alpha I plus 1 P is cross plus omega I cross omega I cross I plus, sorry, I plus 1. Right. So this is the equation of a linear acceleration for I plus 1. Right. So we want to find the tangential acceleration of I plus 1. So this tangential part is given by this. So what we have to find? We have to find this one. So tangential, and this is nothing but angular, or not angular, radial acceleration. So tangential uh, acceleration we have to find. So that is nothing but alpha I cross I plus 1 P, right? So alpha is given, yes. P is given, yes. So you can find that. So we have to take a cross product of what? 0 to 1 cross 2, 0, 1. So how will you do that? So write it down like this, I, J, K. So 0 to 1, 2, 0, 1. That is take I. So like this. So what will get? 2 minus 0 minus j. If you do this way, what will get? 0 minus 2 plus k. What will get? If you like see like this, you'll get 0 minus 4. 0 minus 4. So what will get here? I, 2i minus minus plus. So this is 2j, and this one is minus 4k. So you will get this as 2, 2 minus 4. Right. So this is nothing but a tangential 2 to minus 1. The correct answer for this question is this one, 2 to minus 1. So this is how we'll get tangential acceleration, 2 to minus 1. Moving forward, we have this again the similar question. Now again we are given what? Angular velocity is given. So that means omega is given, omega I is given 0, 1, 2. Then acceleration vector is given. That means alpha I is given. That is 0, 2, 1. And P is given. I plus 1 I. That is 2, 0, 1. Now they have asked for radial acceleration, that is nothing but centripetal acceleration. So going back, all we need is that we want to find this part, that is radial acceleration. So let us write it out here. So radial acceleration, A radial equals to omega cross omega cross P I plus 1 P, right? Not P, I. So how will you find that? First we'll find this and then we'll find the whole thing. So let us first write this thing, I cross P I plus 1. So this is nothing but this is given, yes. P is given, yes. So what we'll get? We'll get 0, 1, 2 cross 2, 0, 1. So this is what we have to find. So if we find this, we write I, J, K, 0, 1, 2, 2, 0, 1. So this is nothing but I. This way it will become 1 minus J. This way it will become minus 4. And K plus K is minus 2. So this is nothing but what we'll get? We'll get 1, 4, minus 2. Right? So this is, sorry, this is the value of this, right? 1, 4, minus 2. So this part we get. So now we have to find I omega I cross 1, 4, minus 2, which is nothing but we have omega again. So that is 0, 1. So 0, 1, 2. That is 1, 4, minus 2. Right? So if we write it here in terms of the I, J, K, what will get? 0, 1, 2, 1, 4, minus 2. So we'll get what? I minus 2 or minus 8. Minus 2, minus 8. Then minus J, and that will be minus 2 and plus K. This is the K, that is minus 1. So this is how you find the cross product. So what will get here? Minus 10I plus 2J minus K. And that you can write as what? Minus 10 to minus 1. Right. So and what we are getting here is minus 10 to minus 1. So this is nothing but the expression for or the value of radial acceleration AR, right? So minus 10 to minus 1. So which one is that here in the option? This one. So this one is correct, right? So this is how you get the radial acceleration, right? So moving on, we have the last question for today. So that is based on backward propagation or inward iterations, the joint force model can be given as how? So which of these equations? So how will you find this or write this? So we want to find the force in terms of I, right? Backward propagation or inward iteration, the joint force model can be given. So FII we want to find. And suppose we are given what? FII is given, right? So suppose there is some link. So if force is given here and there is a force some here, how can you see the load which is transported from here to here? So that is known as backward propagation, because suppose if you have any manipulator like this, and you have an end effector here, and you want to do something, and if suppose like you were cleaning or painting some car or something like that using the arm manipulator, so whatever force you are exerting here, that will have effect on all the joints, right? So basically in this case, what happens that whatever force is applied here, that is generally used to transfer back to the base joints to find the joint force parameters. So this is how it is done. So that's why it is called backward or inward iterations. So now looking into the options, which one should be correct? So we have F, that is the force which is there on the eye, and then there will be the force which will be retraced back from the upward, that I plus 1 to I. So how will you add that? So F I plus, suppose you have force on I plus 1 as F I plus 1, and then you have to multiply the rotation. So I plus 1 to I, right? So we transfer that force from I plus 1 frame to the I, and we have already I, and that is nothing but the force on the ith frame, right? In terms of I. So this is how you can say, or you can find out the force model for ith frame or the ith joint based on the force available on the I plus 1. So, and we understood how that is done and why it is done, because it's very logical also that if you have something force applied here on the end effector or the upper joints that have the effects, and that can be transferred here, right? And that is easy to find using this model, right? So this is the correct model, and so which option is correct? So I think this option is correct. So these are the questions which were given in the last year's assignments. So with this, I would like to end today's session. So I will be uploading this session online tonight. And if you have any questions, you can ask there, or else you can also write in the chat box or comment it there. I will try to answer that. If you have any question now, you can also write it down. Else, we'll end this session for today. Thank you. We'll see you again next Sunday, 3 to 4.
Sir,
Yes,
sir, I have a doubt in assignment 4, sir. In
assignment
question number
4.
11. Yes, sir. Question number 11.
Wait, let me look. Assignment 4, if I have here. Assignment for last year or this year's?
This year, sir. Answer already came, sir, but I have doubt, sir.
Okay, so I have not looked into that part, so I will discuss that in the next class. Actually, I have another work. So you can just tell or remind me next class. Okay, so assignment which for question
Uh,
number?
assi- Question number 11, sir.
Question number 11. Okay, so I will discuss. Any other questions from previous assignments of this year's which you want to discuss? I will discuss in next class. I will make prepare for that as well. Any
Okay,
other
sir. Sir,
questions?
sir, I
You
have
just,
also asked.
yeah, yeah. Go ahead.
I have I have also asked in ask question tab, sir, but no response from that side, sir.
Okay, no problem. I will solve that question. So assignment for question number 11, right?
Yes, sir.
So I don't have this year's question right now. So I will look into it, and I will in the next class when we meet, you just remind me. I will solve this question in front of you. And if you have any other doubts, so in the meanwhile, you can also like if you have any doubts from the previous assignments, you go to the one of the videos in YouTube and you comment it. So I will get a notification that you have some doubts in this year's assignments question number. So I will look into that question. I will try to solve and I will discuss with you. So you list
Okay,
out
sir.
all the question and or else you can write me a mail as well. So my mail ID is you can write out Amit Kumar.
Spelling, sir.
Wait. I will just put that into the chat box, right?
Yes,
That
sir.
will help. Okay, so you just mail me with all the questions. So this year's question which you have doubt, which you have already submitted and you have doubt. So I will not be able to solve the questions which will be you have to submit. Whatever you have submitted, we can discuss that. Understood?
Okay, sir. Okay, sir. Okay, sir.
Okay.
Thank you, sir.
Yeah, so just write me a mail with the questions which you want to discuss, you want me to discuss in the next class. I will discuss that along with the previous year's questions.
Okay, sir.
Okay, thank you. Bye. Have a nice day.